In previous lessons, we've been putting some emphasis on right triangles, and we've just introduced 3 of our basic trig functions, which are sine, cosine, and tangent. Now, we will be relying on what we learned in those lessons to understand some identities of special triangles. What do we mean by special triangle? We've talked about Pythagorean triples in a previous lesson, where we memorized the lengths of the sides of certain triangles that will satisfy the Pythagorean theorem every time, such as 3, 4, 5. However, in this lesson, we will be identifying the special triangles using their angles. With what we learned in previous lessons, we can use this information about the angles to derive side lengths, sines, cosines, and tangents of each of the special triangles we go over in this lesson. These values will become identities, or values that will always be true. These identities will come in handy as we dive further into trigonometry and eventually calculus. As always, let's try to build up some intuition. We know from our lesson on triangle properties that the interior angles of a triangle add up to 180 degrees. We also know from that same lesson that one of the angles of a right triangle is exactly 90 degrees. And that leaves us with a total of 90 degrees to work with for the other 2 angles. 2 natural ways we can break this up are 2 45-degree angles, or a 30-degree angle and a 60-degree angle. Let's start with that first option. Now we will be using what we know about the relationship between corresponding angles and sides. From this property, we know that the smallest angle is opposite from the shortest side, and the largest angle is opposite from the longest side. From here, we can see that angles A and B are equal, so the sides A and B are also equal. We're going to update our labels to keep track of this information. So the angles A and B are equal, so we'll change this to A. And the sides A and B are equal, so we'll change this to A. Now with these special triangles, we are interested in the relationship between the lengths of the sides. So let's say we have that A equals 1. You'll see why we've chosen this measurement in our lesson on the unit circle. From here, we can use the Pythagorean theorem to find the length of C. So we have our formula, A squared plus B squared equals C squared. And then we just plug in what we know. So we have A is equal to 1, so we have 1 squared. We know that B was equal to A, so we have 1 squared again, equals C squared. So now just solving, we have 2 is equal to C squared, and radical 2 is equal to C. So we've just derived our first special triangle. From what we know about similar triangles, we can now use this identity for any right triangle with these angles. Their sides will just be multiples of what you see here. Say you come across a 45, 45, 90 triangle and need to solve for 2 of the sides. You could use this ratio, 1 to 1 to radical 2. And these correspond with the angles 45 degrees to 45 degrees to 90 degrees. We'll do some examples of this later. It may have seemed intuitive to break up a triangle into 45, 45, 90, but why did we choose 30, 60, 90? Say we have an equilateral triangle. From our triangle properties video, we know that this is a triangle whose side lengths are equal and all 3 angles are congruent. This produces the triangle that you see here. Now let's say we cut this in half. As you can see, this creates 2 different right triangles. So let's update our diagram a little bit to reflect these changes. So this angle here becomes 30 degrees, same as this one. And now this side is x over 2, and this side is x over 2. To work with our derivation, let's label this in a way that's a little bit more familiar. So we have our angles A, B, and C. So then labeling our sides, we have A, B, and C. Again, let's say our small side A is equal to 1. We determined that this side is half the length of our hypotenuse C. So we can easily find that C equals 2. Now we just need Pythagorean theorem to solve for our final side, B. So again, we just have A squared plus B squared equals C squared. and then plugging in what we know, we have 1 squared plus b squared equals 2 squared. Rearranging this, b squared equals 4 minus 1, b squared equals 3, b equals radical 3. So now that we've derived this special triangle, we can now use the ratio trick like in our last problem to solve for the missing sides. So using our derivation, we know that this ratio is 1 to radical 3 to 2, corresponding to our angles, 30 degrees, 60 degrees, and 90 degrees. Now that we've derived our second special triangle, let's work with both of them to get identities for our trig functions. This is a simple process using the formulas we derived in our sine and cosine as well as our tangent lesson. From those lessons, we know the following formulas. Sine of an angle is equal to the opposite side over the hypotenuse. Cosine of an angle is equal to the adjacent side over the hypotenuse. And tangent of an angle is equal to the opposite side over the adjacent side. So now let's make these calculations for both of our special triangles. You should notice that we have 2 copies of our 30, 60, 90 triangle on this slide. That's just because we're going to be drawing some arrows and we don't want our diagrams to get messy. So let's start with sine of 45 degrees. So we take the opposite side over the hypotenuse. So we have 1 over radical 2, or if we rationalize, radical 2 over 2. Going with cosine of 45 degrees, we see that we actually get the same answer because our adjacent side is still 1 and our hypotenuse is still radical 2. So we have the cosine of 45 degrees is 1 over radical 2, or radical 2 over 2. Finally, our tangent is our opposite side over our adjacent side. So this is just 1 over 1, which is just 1. Now working with a 60-degree angle, we have that sine of 60 degrees is equal to the opposite over the hypotenuse, so that's radical 3 over 2. Cosine of 60 degrees is adjacent over hypotenuse, so 1 over 2. And tangent of 60 degrees is opposite over adjacent, which is just radical 3. Now finally, working with 30 degrees, we have our sine is opposite over hypotenuse, so 1/2. Cosine is adjacent over hypotenuse, so that's radical 3 over 2. And tangent is opposite over adjacent, so 1 over radical 3, or once we rationalize, we have radical 3 over 3. All of these values are identities, and many of you will be expected to memorize them for your classes. However, now we've shown you how to derive them in case you ever forget during the panic of an exam, and in our unit circle video, we will create a reference table that will be available on our website. So now let's do a few quick examples of the ratio trick we talked about earlier. So we need to find the missing sides of this 45, 45, 90 triangle. So right away, we know that our ratio is 1 to 1 to radical 2. And we see that we have one known side, which is 6. As we said before, every triangle with these angles will just be a similar triangle to what we derived. So all of these values in our ratio are going to be multiplied by the same constant. So we can rewrite it as 1x to 1x to radical 2x. This one's kind of easy since our known side is across from our 45-degree angle. So that means that our x is just 6. So we have 1 times 6 to 1 times 6 to radical 2 times 6. So then once we solve for all of the other sides, we have 6 here and 6 radical 2 here. This one's a little bit more challenging, but still very doable. So in this case, we have a 30, 60, 90 triangle. So our ratio is 1 to radical 3 to 2. So as we said in the previous example, we can rewrite this as 1 times x to radical 3 times x to 2 times x. So now we need to find the value of x. So we can see here that our known value of 9 is across from our 60-degree angle. So that means it corresponds to the radical 3 in our derivation. So radical 3 times x is equal to 9. So now we just do simple algebra to solve for x. X is equal to 9 over radical 3. Rationalizing this, we get 9 times radical 3 over 3. And then simplifying this down even further, we have that x is equal to 3 times radical 3. So now we just plug that into our ratio. We have 1 times 3 radical 3 to, we already know that our middle value is going to be 9, to 2 times 3 radical 3. So our missing sides are 3 radical 3 and 6 radical 3. If you thought this lesson was helpful, make sure you like this video and subscribe to stay up to date on our latest content.